Good morning. Are there any questions? Okay, so let's continue on our discussion. We left off with taking a look at the last example dealing with the Lagrange multiplier. And here's what we have. All right, so it's a supposed Celsius temperature at a point x, y, and z on a sphere, which is defined as x squared plus y squared plus z squared equals 1, is t is equal to 400 x, y, z squared. Locate the highest and the lowest temperature on the sphere. Okay, so in this example, we are given our sphere. And the sphere is defined as, again, x squared plus y squared plus z squared equals 1. And then we are given a formula for the temperature. So T, which is equal to 400 x, y, z squared. Okay. So what we're trying to do is to find the highest and the lowest temperature. Okay. So if we take a look at this particular problem, all right. So for the first one, we're going to rename this. Okay. So since we're working with a sphere, we're just going to call it S. And we're going to say that's going to be equal to x squared plus y squared plus z squared not equal, but minus 1. Okay. And the second equation is already set up for us. Okay. So if we're going to use the Lagrange multiplier, so the first thing we're going to do is we're going to find the gradient of t. Okay. So if we find the gradient of t, all right, so the first component is going to be doing the partial in respect to x. So if we do that, we're going to end up with 400 yz squared in the I direction plus the second is going to be the partial in respect to y. So it's going to be 400 xz squared in the j direction plus, and then the last component is going to be the partial in respect to z, which is going to be 800 xy in the k direction. Any questions there? All right. So next, what we're going to do is to look at the partial in respect to s. Okay. So for the first component, what would the partial in respect to s be if we take in the partial in respect to x?
Sorry, in the k direction of the first one, I think there's c as well.
Say that again.
Sorry, in the first derivative, like in the k direction, I think there's c too, right? Like after taking the derivative.
Oh, yeah.
800 x, y, z, right? Yeah.
There we go. Yes. Okay. All right. So first component would be 2x in the I direction. The second component will be what?
2y in the j direction.
Okay. And the last component will be what?
2z in the j direction.
K direction. Okay. So again, keep in mind that we're taking a look at the equation for the Lagrange multiplier. So it's going to be the gradient of t is equal to lambda times the gradient of s. Okay. So if we write our equations, So we're going to basically have three equations that are going to come out. Okay, so our first equation is going to be that 400 yz squared is equal to 2x lambda. Our second equation is going to be 400 xz squared, and that's equal to 2y lambda. And then our third equation is going to be 800 xyz, and that's equal to 2z lambda. Okay, so what we're going to do, all right, okay, so if we look at these equations, would it be ideal to solve for the variable either x, y, or z? So if you look at these equations, would it be ideal to solve for an equation in terms of x, y, or z? So let's think about this. If we are able to solve for a particular variable, and we can do a substitution back in, would it be easy to do that? And it probably will not, because the variables are kind of all screwed up. So since we don't have the situation that we can solve for x, y, and z easily, okay, why don't we try to get rid of the extra variable of lambda and see what we can do with that? Okay, so let's look at this first equation here. So what I'm going to do is to solve for lambda. So if I solve for lambda, I'm going to end up with 200 yz squared over x. I'm going to call this lambda 1 just to kind of distinguish between. Okay. Let's do the exact same thing with the second one. So if we do that, we're going to have that lambda is going to be equal to, and we're going to end up with 200 xz squared over y. I'm going to call this lambda 2. Okay, so basically I found two different expressions for lambda. And what I'm going to do is I'm going to use each one of those different expressions for lambda and put it into the third equation. Okay, and see if I can get some things to solve out. Okay, so let's start off first using lambda 1. All right, so if I do that, I'm going to end up with 800 xyz is equal to 2z times, in place of lambda, we're going to put in 200 yz squared over x. Okay, So what I'm going to do in order to solve, I'm going to multiply both sides by x, and then I'm going to multiply through. So if I do that, I'm going to end up with 800 x squared y z, and this is going to be equal to 400 y z cubed. So now, if I want to solve this, basically I want to get it equal to 0. So I'm going to have 800 x squared y z minus 400 y z cubed is equal to 0. Now, once I get it here, what can I do?
Factor out 400 yz.
400 yz, good. And then we're left with 2x squared minus z squared, and this is equal to 0. So what we can do is we can set each factor to 0. So we have 400 yz is equal to 0, or we're basically going to have that yz is 0. Okay. Then the other piece, we're going to have that 2x squared minus z squared is equal to 0, or we can have that z squared equals 2x squared. Okay. So what we're going to do now is take a look at each of these conditions that come out from lambda 1. Okay, so if y times z is equal to 0, okay, so kind of the easiest way we can look at this is by just saying that both y and z are 0. Okay, so if we let y and z equal to 0, okay, so what we need to do is to find x. So in order to help us find x, we're going to use the sphere. So we're going to use x squared plus y squared plus z squared equals 1. Okay, so if we let x, y, and z be 0, we're going to end up with x squared plus 0 squared plus 0 squared equals 1. So that means that x squared is 1. So what's x going to be equal to? Plus or minus 1. Okay, so that's going to generate a point, and our point, and it's actually 2 points, it's going to be plus or minus 1, comma, 0, 0. Any questions there?
Can you go back to the slides? Right, thank you.
Mm-hmm. Okay, so now we're going to take a look at this second condition where z squared is equal to 2x squared. Okay, so if we take a look at, let me see here. No, I'm not ready to look at this condition yet. Okay, I am going to come back and look at it, but just not right now. So what I'm going to do now is now I'm going to use the second value, the second expression I got for lambda, and I'm going to plug it in. Okay, so let's do that. So we're going to have 800 x, y, z, and this is going to be equal to 2z times. Now, our second lambda was defined as 200 xz squared over y. So the same thing I'm going to do is I'm going to multiply both sides by y, and then I'm going to multiply the right-hand side out. So if I do that, I'm going to have 800 xy squared z is equal to 400 xz cubed. So I'm going to do kind of the same approach as what I did with the last one. So I'm going to get this equal to 0. So I'm going to have 800 x y squared z minus 400 xz cubed is equal to 0. Now once I get it here, what can I do?
Factor out 400xz.
Okay, so if I factor out a 400xz, I'm going to be left with 2y squared minus z squared equal to 0. And again, what I'll do is set each factor equal to 0. So I have 400 xz is equal to 0. So we can say that xz is 0. And the other piece, we're going to have that 2y squared minus z squared is equal to 0. And z squared equals 2y squared. Okay. So what we're going to do is just like we did last time. We're going to start off looking at this condition. Okay. So if we take a look at that condition, okay. So now what we're going to do in this scenario, we're going to let x and z be equal to 0. Okay, so we're going to solve for y. And again, we're going to use the the sphere to help us out with that. So we're going to have that x squared plus y squared plus z squared is equal to 1. So we're going to have that 0 squared plus y squared plus 0 squared is equal to 1. Y squared is 1. So what's y going to be?
Plus or minus 1.
Okay, so we're going to get plus or minus 1. So we're going to get the point 0, comma, plus or minus 1, comma, 0. Okay, and keep in mind that it is two separate points. Okay. Any questions? Okay, so what we have left is we have our equations. We have these equations here. This one and this one. Okay. So if we're taking a look at that, those two equations, basically we're saying that z squared is equal to, say, the other variable. Okay. But let's keep in mind that z squared can only be one of the particular variables at once. It can't be both at the same time. So is that going to be able to help us be able to solve for a variable in the solve for a value in the sphere, since z squared is equal to two different expressions? Okay, so this is the question I'm basically asking.
Do you mean the value of x and y?
Well, I mean, and it may not be for just x and y, it could be for anything. Okay, Moses, you say yes. What can we do in order to be able to solve for a particular variable? And which variable, well, let me say, which variable do you want, which variable would you be trying to solve for? Okay, so we can solve for z. So let's do that. So in place of x, we can replace that with what? Excuse me, x squared. We can replace that with what? All right, so we can replace that with z squared over 2 plus, in place of y squared, we can replace that with what? Z squared over 2 plus, then we're going to have z squared equals 1. Okay, so let's make it easy. I'm going to multiply everything by 2. So I'm going to have z squared plus 2z squared equals 2. Or we're going to have that 4z squared equals 2. So that means that z squared is equal to 1/2. So what's z going to be equal to?
Plus or minus 1 over square root 2.
Okay, so plus or minus 1 over the square root of 2. All right, so we found z. So now we can find x and y. So we can say that x is going to be equal to, well, let me back up a little bit. So we know that x squared is equal to z squared over 2. So that means that x squared is going to be 1/4 over 2. Excuse me, not 1/4. Step too fast. So we're going to have 1/2 over 2, which is the same thing as 1/4. So what's x going to be equal to? Yes, plus or minus 1/2. Okay, and then for y squared, we know that y squared is z squared over 2. So we know that y squared is going to be 1/2 over 2. So that means y squared is equal to 1/4. I mean, y is going to be plus or minus 1/2. Okay, so kind of our point that we have going on here, right? So we're going to have plus or minus 1/2, plus or minus 1/2, plus or minus 1 over the square root of 2. Okay. And keep in mind that this represents like 8 point. This represents 8 points. It's not just 1 point. Now, keep in mind that in this problem, we were asking to find the highest and lowest temperature on the sphere. Okay, so what we need to do is to check. So we're checking the points that we found. So we found 2 points, which is plus or minus 1 comma 0 comma 0. We've got another, which is 0 comma plus or minus 1 comma 0. And then we got the final one, which is plus or minus 1/2, plus or minus 1/2, plus or minus 1 over the square root of 2. Okay. Now, our temperature formula was that T is equal to 400 x, y, z squared. Make sure I wrote that correctly. Okay. So for the first one, no matter if it's plus or minus on the x, T is always going to be equal to what? That's going to be 0. Okay. For the second point, no matter if it's plus or minus 1 on the y, T is always going to be equal to what? That's going to be equal to 0. Okay. Now, for the last one, okay, we're going to get some different values. We're not going to get 0. Okay. So we want to look and see which one is going to be the smallest. And then we want to look at the largest. Okay. Now, as far as the smallest is concerned, it's not z that's going to determine. It's going to be determined by x and y. Okay, so we can look at one scenario where x is positive, y is negative. Okay, so if we take a look at that, we have t is equal to 400. We're going to have 1/2 times negative 1/2 times 1 over the square root of 2 squared. Okay, so we're going to end up with 400 times, if we square that, that's going to be 1/2, and multiply that. So we're going to get negative 1/8. So we're going to end up with a value of negative 50 degrees. Okay. Any questions there? And then for the largest, again, z is not a factor because it's always going to be squared, so it's always going to be positive. So we need both, either x and y both have to be positive, or both x and y have to be negative. And it doesn't matter which one we check, we just want to look. So let's just look at the situation where they're both positive. So t is going to be 400 times, we're going to have 1/2 times 1/2, and then we're going to have 1 over the square root of 2 squared. So we're going to have 400 times 1/8. So we're going to end up with 50 degrees. So where I've got the highest, that's the largest, that's going to be the highest temperature, which is going to be 50 degrees Celsius. And where I've got the smallest, this is going to represent the lowest temperature, which is going to be negative 50 degrees Celsius. Now, in this problem, it didn't ask us to specify at what point these occur. They just want us to find the temperature, which makes it a little bit easier, because if we had to identify every possible point, it takes a little bit longer. Any questions? Okay, well, that is the end of the section dealing with the Lagrange multipliers. Okay, are there any questions? Okay. All right, so at this time, this kind of ends the portion of the course which deals with differentiation. So now we're going to move into integration. Okay, so the first section we're going to take a look at dealing with integration, we're going to look at double and iterated integrals over rectangles. Okay, so we're going to look at double and iterated integrals over rectangles. All right, and the first thing we're going to talk about is something that we refer to as the Fubini's theorem. Okay, and what this theorem says is this: it says if f of xy is continuous through a rectangular region, where the region is defined that x is bounded between a and b, y is bounded between c and d, then what this is saying is that if I do the double integral over this region of the function f of xy dA, okay, so what this would be equal to is going to be the integral. We can go from c to d, integral from a to b of f of x comma y dx dy, or we can look at this as the integral from a to b, or the integral from c to d of f of x, y, dy, dx. Okay. So what this is doing, this theorem is allowing us to be able to do a double integral, which also can be referred to as an iterated integral, over basically a rectangular region. Okay. All right, so what we're going to do first is to take a look at how this will work. Okay, so let's take a look at some examples. So the first example we have is this. I want to find the integral from 0 to 2, then the integral from -1 to 1 of x minus y dy dx. Okay, so if I do this problem, all right, so whatever is first, this tells me this is what I'm going to integrate in respect to first. Okay, so if I do this, what I'm going to end up with is I'm going to have the integral from 0 to 2. That stays. Now, what I'm going to do is take the antiderivative of this in respect to y. So if I do that, I'm going to end up with xy minus 1/2 y squared. Then I'm going to evaluate this from -1 to 1. And then I need to, after I get this value, then I need to integrate in respect to x. So what I'm going to do first is to evaluate. So I'm going to have the integral from 0 to 2. If I plug in 1, I'm going to have x minus 1/2. Minus, if I plug in -1, I'm going to have negative x minus 1/2. So if I clean this up, I'm going to have the integral from 0 to 2 of just 2x dx. Now, if I integrate this in respect to x, I'm going to end up with x squared. Then I'm going to evaluate it from 0 to 2. And if I plug in, I'm going to have 4 minus 0. So I get a value of 4. Okay. Any questions? Okay, so now let's look at the next example. So the next example, I'm going to have this. I've got the integral from 0 to 3, integral from -2 to 0 of x squared y minus 2xy dy dx. So by looking at this, the first time what we're going to do is we're going to integrate in respect to y. Okay, so if I integrate in respect to y, I'm going to have integral from 0 to 3. So what would be the antiderivative of the first term in respect to y?
One half x squared y squared.
Squared y squared, good. Minus, what's the antiderivative in second term in respect to y?
Minus x y squared.
Yes. But we're going to evaluate this from -2 to 0, and then we're going to integrate in respect to dx after we do that. Okay. Any questions so far? Okay, so now what we're going to have is we're going to have the integral from 0 to 3. Okay, so if we evaluate this at 0, we're going to get 0. Minus, if we evaluate it at -2, we're going to end up with 2x squared minus 4x dx. And always, I recommend going ahead and simplifying before trying to integrate again, just to make your life easier. So really, what we're going to have is the integral from 0 to 3. So we're going to be integrating -2x squared plus 4x dx. So if we find the antiderivative of this, what do we get?
-2/3x cubed
Oops. So -2/3 x cubed
and 2x squared
plus 2x squared. We're
from
going to
0.
evaluate from 0 to 3. So if we put in 3, right, we're going to end up with -18 plus 18 minus, if we plug in 0, we have 0 minus 0. So we're going to end up with 0. Any questions? Okay. All right, so let's look at the next example. All right, so the next example we have this. We have the integral from pi to 2 pi, integral from 0 to pi. And we have sine of x plus cosine of y dx dy. Okay. All right, so what I'm going to do is I'm going to give you guys a couple of minutes to work that out and see what you get. All right, so let's take a look at this example. All right, so the first time we're going to integrate in respect to x. Okay, so we're going to have the integral from pi to 2 pi. So when you integrate in respect to x, what did you get?
Negative cosine x plus a cosine y.
And we're going to evaluate that from 0 to pi. Okay. And we're going to integrate in respect to y. So we're going to have the integral from pi to 2 pi. All right, so when we plug in pi, what values did you get? So when you plugged in pi, what did you get?
1 plus pi cosine y.
Okay, minus. And now when we plug in 0, what did you get?
1 plus 0.
Okay. All right, so we're looking at integral from pi to 2 pi of what?
Pi cosine y.
Let's be careful. At 0, what should you get when you evaluate above at 0? Yes, it should be -1. Okay. All right, so now if we clean this up, what should we get?
Oh, 2 plus pi cosine y.
And we're going to integrate in respect to y. So if we integrate in respect to y, what do we end up with?
2y plus pi sine y.
And we're evaluating from pi to 2 pi. Okay. So if we evaluated 2 pi, what value will we get?
0. I mean, like 4
No.
pi plus 0.
Yeah, so we're going to get 4 pi plus 0 minus, if we evaluated pi, we're going to get what?
2 pi plus
And
0.
again, plus 0. So our final answer is going to be what?
2 pi.
And that's our answer. Okay. Any questions?
I have a question. So we did the integral of sine x plus cosine y. So we, in respect to x first, right? And then, so we treat cosine y as like a constant, kind of?
Yes.
Okay. Yeah, I was confused in that part. I was like, oh, I missed that.
So
Okay.
that would be treated as a constant. So it's the same principle as when we are doing partial derivatives.
Mhm.
If we're doing the partial derivative of xy in respect to y, that means x is a constant. It would be treated as a
Okay.
constant. So same principle.
Okay, thank you.
Any other questions? Okay. All right. So let's move to our next example. Okay. In the next example, it wants us to evaluate the double integral over the given region. So in the first one, we are asked to do the double integral over the region of x over y squared dA, where the region is defined as follows: is x is bounded between 0 and 4, and then y is going to be bounded between 1 and 2. Okay, so now what we're going to do is to just set it up. So we're going to have the double integrals of our function. Now we just got to decide, what do we want to integrate in respect of? Do we want to integrate in respect to x first, then y, or y, then x? So how do we want to integrate? Who do we want to go first, x or y?
I guess x.
Okay, so if we do x, so we're going to do dx dy. Since x is first, that means we're integrating from 0 to 4 on the inside integral. On the outside integral will be from 1 to 2. Okay, so now let's integrate first in respect to x. So we're going to have the integral from 1 to 2 of, now 1 over y squared, that's a constant. We're going to multiply. So what's the antiderivative of square root of x? Yes, so it's going to be 2/3 x to the 3/2. All right, now we're going to evaluate this from 0 to 4, and then we're going to integrate in respect to y. So if we evaluate this at if we evaluate this at 4, what value will we get? We get 16/3. Minus, if we evaluate it at 0, what will we get?
0.
0. So what we're going to end up with is the integral from 1 to 2 of 16 over 3y squared dy. Now, keep in mind, 16/3 is a constant, so we can pull it out. So what's the antiderivative of 1 over y squared?
Negative 1 over y.
Okay, so we're going to have negative 1 over y, and then we're going to evaluate that from 1 to 2. Okay, so we're going to have 16/3 times, at 2, we're going to have negative 1/2, minus at 1, we're going to have negative 1. So we're going to have 16/3 times, so what's negative 1/2 plus 1?
Positive 1/2.
So what's our final answer?
8 over 3.
Okay, 8/3 will be our answer. All right. Any questions? Okay. All right. Let's look at the second example. So the second example, we have this. We have the double integral over the region that is defined as xy e to the xy squared dA. And we have a region defined as x is between 0 and 2. Y is going to be between 0 and 1. Okay. So what I want you to do is I want you to set up the double integral and evaluate it. Okay. For this particular problem, when you get done, you should end up with this. Okay. No, it doesn't really matter if you put x first or y first. You're going to see that, like right now, it's not a big issue, but you'll see later on that sometimes it's going to be easier to integrate in respect to the other variable first before you integrate in respect to the other one. Okay. You're going to find that you're going to be able to do the problem one way, but not the other. You actually kind of get a taste of that on this particular problem. Okay, so I'll give you a couple of minutes to get that worked out and everything, and then we'll talk about it. Okay, so let's take a look at this particular problem. Now, in this problem, we are going to have to be careful of how we set this up, because one way we're not going to be able to do it. And well, we'll be able to do it, but it's kind of tedious. But the other way is really easy. Okay, so the way I'm going to set this up is I'm going to have my double integral. Okay, I'm going to have xy e to the xy squared. Okay, I'm going to do dy then dx. Okay, So I'm going to have from 0 to 1, then I'm going to have from 0 to 2. Now, the reason why I want to do y first is because it makes it easier for me to do my u substitution. Okay? Whereas if I do x first, if I take the derivative of the exponent, okay, if I take the derivative of the exponent, it's going to be y squared, but I don't have a y squared in front. So that creates a problem. So this is why I want to do the other way. Okay. So with this, if I do integrate this in respect to start y first, I'm going to have the integral from 0 to 2. And when I do this, is again a u sub, so u is going to be xy squared. So that means du is going to be 2xy. I've got the xy missing the 2. So that means I'm going to bring out a 1/2, and then the antiderivative of e to the u is just e to the u. And I'm going to evaluate from 0 to 1, then dx. So if I evaluate this, it can become the integral from 0 to 2 at 1. At 1, I'm just going to have e to the x. At 0, I'm going to have 1 in dx. Okay. And now what I'm going to do is integrate this in respect to x. So if I do that, I'm going to bring out the 1/2. Antiderivative of the first term is e to the x. Antiderivative of 1 is x. I'm going to evaluate from 0 to 2. So at 2, I'm going to have e squared minus 2, then minus. At 0, I'm going to have 1 minus 0. And when I combine like terms, I end up with this expression here. Any questions? Okay. All right, so let's take a look at our last example in this section. So the last example we have is this. We have that we want to find the volume of the region bounded above by the surface z equals 4 minus y squared and below by the rectangle that's defined. R is defined as x is bounded between 0 and 1, y is bounded between 0 and 2. Okay, so in this region we have our surface, we have our region, okay, and we want to find the volume. All right, so for the volume, we don't have to do anything fancy, okay? If you take the double integral of a function, this is volume, okay? So if you take the double integral of a function, you're finding volume, all right? So what we're going to do is to have our double integral, okay? Our function, which is defined as 4 minus y squared, okay? Now, in this particular problem, if you notice, there's no x values in here, okay? So x is really, so it really doesn't matter how you integrate this, if you integrate with respect to x first or y first. I'm going to do y first because everything's defined by y. And once I do y, I know that when I get ready to do x, this is an easy it's going to be easy. So I'm going to do dy dx. Okay, and it doesn't matter if you did dx first and then dy, you're still going to end up with the same answer. Okay, so for the integral, I'm going to go from 0 to 2. For the outer, I'm going to go from 0 to 1. So the first time I'm going to integrate in respect to y. So I'm going to get that 4y minus 1/3 y cubed, evaluated from 0 to 2. So if I evaluate it from 0 to 2, at 2, I'm going to have 8 minus 8/3. At 0 is 0, so I'm going to ignore that. So I'm going to have the integral from 0 to 1. This is going to give me 16/3 when I subtract that dx. So when I integrate this, it's going to be 16/3 x evaluated from 0 to 1. So I get 16/3. Any questions? Okay, so I'm going to stop here for today. Okay, so a couple of things that you need to make sure you are working on. You need to make sure you are working on the Lagrange multiplier homework. Okay. Also, the double and iterated integral, and I can spell integral correctly. Homework. Okay, so you need to be working on those. Also, quiz 10 is available. It's due Thursday. Okay, quiz 10 is available and it's due Thursday. All right. Now, as far as your midterms are concerned, I am working on grading those. I've got like 3 or 4 graded, so I've got a couple more left to finish up. So you should be seeing those grades pop in over then you'll probably see some more pop in. Your grade possibly will pop in today, or it will pop in tomorrow morning. Okay. Any questions? All right. Again, you need to be working on this homework. I do have the solutions posted in those on those things, so make sure you pay attention to those. Please, with the integration homework, try to keep up because we're just going to keep compounding on things as far as the integration is concerned. So make sure you keep up on that homework. All right. You guys have a great rest of the day, and I will see you on Thursday.